All right, so this is going to be the last lecture on security. I want to wrap things up. Inevitably, I can't talk about everything, right? So I just want to touch upon some other issues, especially what do you do with all that nice cryptography that we discussed. One of the main applications is going to be access control, right? And we already discussed some of the issues involved in this. I mean, cryptography can be used at the low level to basically just send secret messages, but as I mentioned at the end of last lecture, by using challenges, cryptography in various forms can actually be used to make sure that the person at the other end is who they claim they are, right? So either in the form of digital signatures, that's essentially unforgeable messages, or challenges or things of the sort, you could start thinking about, can I come up with some sort of an elaborate mechanism to allow possibly fine-grained access to resources, right? So access control, it's all about controlling who can do what on which of the resources. And you can detach yourself a little bit from it. It doesn't matter what the resource is. In principle, you have some sort of a subject that's going to make a request for an operation, some monitor in the middle that might or might not authorize a request, and then you can do a certain operation on the object. Now, what's important is to make sure that when you get authorized, there's some sort of an unforgeable authorization. I mean, ultimately, somebody has to do something on your behalf, right? So these issues are actually very old. It's multics in 1960s. The moment you have more than one user on a single machine, there's multi-user systems. When they started having dumb terminals on top of a larger computer, you have to be worried about who can do what, right? So it started first with things like files and access to files, and this is where all the stuff about permissions on files actually comes from. But you probably already had your own frustrations about sometimes the file permissions are not detailed enough to really allow you the kind of control you would like to have, right? And that led to more sophisticated solutions, all of them around some sort of access control list, access control matrix, access control something else, right? Those are replacements of just the very low-level crude permission style access control. But all of them require a fundamental mechanism, which is how do you authenticate somebody, right? So authentication is part of the game, and on top of authentication, you have to map this particular, let's say, person to the fine-grained rights that they have, right? So it always has to go in multiple steps. It doesn't have to be a person, by the way. It's another entity, right? So you first authenticate, and then you're going to have some sort of a way to compute the rights. Okay. Now, even when it comes to authenticate, the question is, how often do you do that? How do you do it? Do you do it on every request, for example? Right? So what I mean by that is, for example, in normal operating systems, you log in into the operating system, and then you have the ability to do whatever for a relatively long period of time until your session expires. But what exactly does it mean for a session to expire? Now, all of these questions are very important, especially when you go a little bit beyond normal operating systems in which you have a terminal and you log into it, right? So suppose you have a web client, and you still have to authenticate with respect to some sort of a server that's going to have some resources that you need access to. And then the question really is, okay, at what point do you expire things? At what point do you force people to log in again? How often do you force people to reprove that they are who they are? Now, all of these things are extremely relevant because one particular kind of attack revolves around the idea that you let a legitimate user log in, but then you hijack the session, and you're going to ride on their session, right? So all of those things need to be taken care of when it comes to authentication and some sort of a session management. So it's not only login here. Login is important if that's the way you want to do it, but also some sort of a session management. So, for example, even with respect to a session, how would you maintain some sort of a session? Well, you see, it doesn't matter how good your authentication is if your session itself is not particularly secure. That's what you would attack. I mean, if you could forge a correct session ID that the server would recognize, or if you could guess the session ID that the server would use in the normal course of operation, then that it's a point of attack, which is actually much easier to implement than, in fact, breaking the cryptography. So keep in mind that almost all the security attacks have nothing to do with breaking the encryption. They have to do with finding loopholes into how the security mechanism was put together, right? So you could do session management, for example, by essentially having a session identifier. And let's say you take the identifier and make it 1, 2, 3, 4, 5. That clearly is going to be a disaster, right? Because then the session identifier itself becomes very predictable. And all you have to do is try to guess what the session identifier might be until you get lucky and the session is correct, right? So the session management, session creation and checking and so on, in fact, pushes the authentication from the user to some automated mechanism. And you need to revalidate the session. This is what most systems will do. The session gets revalidated on every request. So what you're doing is you're going from a mechanism that requires some sort of a user intervention, potentially, with the login, to something that can be fully automated but expires. So, for example, most of the web applications right now, the reasonably well-written web applications, upon some sort of a user login, will create a secure session ID. And that secure session ID is checked every time. You check the validity of the session ID to make sure it's a genuine session that you do know about and it's tied to a particular user. But the validity of that session, it's checked on every single request. So if you need to pull 10 images, let's say, from the website, and you don't want people to have access to those images unless they have the right privileges, right? Only certain users, let's say, can see those pictures. You would, in fact, revalidate the session on every single request. And that's the only way to do it in order to be secure. So this is kind of a general principle. One mechanism to mitigate the need for a heavyweight mechanism, like logins, is to basically cascade through security mechanisms, through cryptographic methods, this kind of authentication and do some sort of a delegation, right? So once you authenticate, you create a secure session, you put an expiration time on it, but then you use the secure session instead of the login on minute operations that you actually have to do. But you will check on every single request something. If you don't, that potentially can actually be exploited. Now, to a large extent, that's what happens in traditional operating systems, where if you log in, but it's a much simpler thing and it's not cryptographically secure. If you log in, you basically just have the right bits in some data structure maintained by the kernel for that particular user. And on every single request, every single system call, the kernel will verify, oh, all right, so for this user, do you have access to this resource or you don't have access to this resource? So the normal, if you want, course of operation in order to reduce, if you want, user fatigue, don't log in on every single request, and to still have reasonable speed and so on, is to do this kind of a delegation. And this is more of a trust delegation. You're essentially going to delegate the ability to access or not access resources to this secure session management, right? Which basically immediately means that, you cannot, well, controlling when you revoke or you don't revoke user privileges has to be tied out with the session management. So you must have the ability, for example, to expire sessions at will on the server side if you really want to have fine-grained control. That's usually not a big problem because these secure sessions are created with secure random number generators most of the time, and they are reasonably large. They mostly go in cookies, for example, right? But other possibilities exist. And then on the server side, you're going to keep a pool of what are valid session IDs to what users they actually correspond, and then you're going to toss them away, okay? And you can revoke any right by just tossing away one of the secure session managements. Now, possibly, if you use the kind of public key cryptography that I talked about last time, you could do another kind of validation, right? In which, for example, you would establish a secret key at the end of the protocol and use that secret key to actually authenticate. It's the trouble with session management in the style I just described, namely you store it on the server for the life of the session, is somebody can attack the server, get an idea of what's in the session management, and then potentially try to access the server from outside using the same session management. Well, I mean, once you attack the server, presumably you can get the files yourself without the session management, but that's not always the case, right? So all of these mechanisms, all of these protocols, you gain some, and potentially you have some darker corners. So this session management, it just crossed my mind. It might matter in the following kind of situation in which a completely different server, it's actually doing the authentication, and other servers are actually executing whatever actions you want on resources. In that case, by breaking into the login server and stealing in-flight session management keys, you could potentially then pretend and go to other servers and run some sessions. So they're all vulnerable to some sort of attacks, especially very directed attacks on the machines that actually run all of this software. Okay? As always, you have to balance convenience and convenience, performance, and security in these kind of circumstances. If you want a truly secure system, possibly it's going to be very annoying to use, right? So but an interesting example is, for example, when do you escalate writes in a normal operating system? So, for example, Windows has a bad reputation that lots of viruses exist and lots of things. And a lot of that has to do with the fact that almost any user, when you install the operating system in a normal way, almost any user is in fact super admin, or admin, depending on the names used for the operating system. And that basically means that any program that download, they can install globally in the system. So the damage can be global. How could you protect against this? Well, you could require, in fact, some sort of a trust escalation or rights escalation. This is, for example, what's happening in Unix operating systems, and probably most prominently on macOS 10. Right? This is why you're prompted, for example, for a password. So when you're prompted for the password, is type the admin password, which could actually be the user admin, rights escalation is happening, right? Now that can be done in a very elegant way and a very secure way through a single choking point. This is in fact happening deep in the operating system as well. We didn't have time to talk about what's inside the operating system and what's not. But the fact that all the system calls go through the same choking point, that means you only need to check writes, or you need to be paranoid through that point through which everything goes through. So when it comes to write escalation, for example, you can use programs like sudo, and all you have to worry about is this sudo program secure? Because everybody will go through the sudo program to actually escalate writes. Escalating writes really means I only have a certain privileges, but by providing a password or some other kind of authentication, I can at least temporarily become a user that has a lot more privileges. Okay? In particular, a super user. Right? Usually, these strangulation points, these programs, will expire the session quite fast. There, you need a session as well, because otherwise, for every tiny operation, and you can have thousands of those, for every tiny operation, you would need to re-authenticate. So this idea that you authenticate and then for a while, things are good, the writes are escalated, right, has been used in various forms in many, many different places, most prominently in operating systems, and now it's used on the web. So you're always looking for both a good way to authenticate and a good way to have some sort of a session management, at least for a while, to keep things actually going. Okay? Now, and they are actually different issues. Session management is more a matter of what happens in the back end, but with some support in the front end. I mean, you must remember the session ID and send it on every request. I mean, that's kind of the idea. Okay? All right. Authentication, we already touched upon some of these issues, right? So one way to do it is really the 99% way, right? You put a password in, and the server takes the password and then compares with the password stored in a database. Now, this can be done in secure ways by essentially computing some sort of a secure hash, like SHA-1, SHA-256, salted, so global attacks are harder. And obviously, the computation of the hash has to happen on the server, and that's one of the vulnerabilities, in fact, right? So this is the client, and this is the server. In order to do a password-based authentication, the password has to cross the boundary between the client and the server. Now, you could use a secure communication channel like SSL, but nevertheless, the server, at least temporarily in memory, has the password in the clear, which actually means that somebody sitting on this machine could eavesdrop and find that password. Now, how practical that is, it's a different question, but the password is there. Okay? And so clear password in this kind of a circumstance, right? Now, of course, here, as fast as possible, what you would like to do is take the password, compute the hash, compare, and once the comparison is true, you, in fact, create a session to say, whoever has the secret session ID, or whatever mechanism you have in there, is, in fact, this person. And then you can use the specific authorization method for specific request, right? The rights management to allow or not allow access to fine-grained resources. Right? Now, let me just remind you the method. I mean, one of the things we discussed last time was a scheme in which once you have the public key here, so let's use the notation KA plus here, I could have, in fact, KA minus here, and simply say, give me a challenge and I'll respond to the challenge. The challenge is a throwaway, temporary thing. Right? So it's still based on, I need to guess something secret, but it's something random used once and thrown away, and it's quite large. Right? So the way the protocol can work is you say, I am, you send only the message, I am A, and the server says, OK, great. Then pick some kind of a random number. Right? You just use your secure random number generation. Random number, and then you send back K plus of R. Right. Now, presumably, K plus of R can be unpacked on the other side only if you apply K minus, KA plus of R. KA minus of KA plus of R, which will give you R. And then you can send it in the clear back to the server. Now, the server it just has to remember temporarily what was the challenge and say, ah, yeah, good. You pass. Okay? And then you toss it away. Now, you could, for example, I mean, even if you eavesdrop on the server, you could find R. If you're faster than this server, possibly you can squeeze something in very fast because you know R and you tell somebody that you have R. But presumably, if you broke into the server, you already escalated more writes than what you had before. So there is maybe a very shallow window in which things might or might not work. You could enhance the scheme by not doing a simple random number there. I mean, making sure that the random number cannot be used more than once or something, right? So there is always a little bit of a window, but if it requires very careful timing and whatnot, it's harder to exploit. Okay? But it's clear how this goes. The important thing here is to realize that the secret key never leaves this machine. Right? That's important. And the public key cannot be used to derive the secret key. This is the basic principle in public key cryptography. Now, one thing that's usually done in security classes is all kinds of mechanisms, and I have, for example, one more, secure key exchange, Diffie-Hellman secure key exchange. All kinds of mechanisms are taught that can be used to establish, for example, a secure key for communication or things of this sort. All of them got fundamentally simplified by the public key cryptography mechanisms, right? Remember how complicated something like Kerberos was, with all kinds of exchange, all kinds of messages, all kinds of things. This one, it's easy. As long as you trust the public key, you're done, right? You just encode challenges with the public key to get things done on the other side. And it goes the other way around, and it's implemented through the SSL certificates, right? Also, I need to reinforce this over and over again, because I think it's very important. If, at least partially, you could use existing mechanisms to provide the security, use the existing mechanisms. Actually, the low-level parts you should never design on your own. You should just find pieces and assemble them into some sort of a security protocol for your application and never design the low-level cryptography, the low-level things. Right? So, I mean, just kind of an interesting story. We had some trouble getting the public key cryptography to run in JavaScript to talk to our backend. And as of yesterday, we actually have exactly this protocol implemented. And the temptation for one of the developers was, I'm going to implement my own version of decryption here or something to make them talk to each other. And I said, no, it's out of the question. We have to use packaged things, because then I have to worry about, did we introduce some sort of a backdoor that we don't even realize in the protocol, right? OK, so let's talk a little bit about how would you do the rights management, because this only allows you to say, you are person X. How do you map? And you can think about this problem as a mapping problem. How do you map the fact that I am person, whatever, X, into what I can and what I cannot do? Okay? And this turns out to be tricky because of performance issues. So let's ignore the security aspect. I already got some sort of a secure session management that lives for at least a couple of minutes or maybe days or whatever. And essentially, the session management is tied in a secure way with who I am. So if I present this certificate, the system knows temporarily that I am that person. But still the question is, when I say I want to access this resource, how does the system determine reasonably fast, yes, you can access or you cannot access that resource? So let's toss away some ideas of what could actually be done. And to some extent, that's going to trace the kind of ideas used in operating systems and now maybe used on the web to do such things. So any questions about this? Again, this stays here. And you can even encrypt it with a symmetric cryptographic method like AES. So then you require a password, but the password is only used to decrypt the private key here to do the exchange, and then you're done, once you have some sort of a certificate that you're good. I mean, for example, a session, classic session management. Session management, by the way, it's extremely well understood. Okay? Now, password security is well understood also, but you're always vulnerable to direct attacks if you store all the passwords in here. Right? One of the problems, before I even go to the other issue, one of the problems is if you steal encrypted passwords, you can take your time at decrypting them, and you can dedicate enormous resources at decrypting them. A system is much, much stronger if you have to do something while the server is in flight. So for example, if you want to steal this R, having a million computers won't help you, because it's a matter of the timing and the right kind of a thing in here. And any attempt to steal it might produce very weird traffic. Right? So you could try to beat, for example, the web browser at some of these tasks and steal something and do something, but then you're going to see it in the traffic, and you're going to be potentially caught in the act of trying to break into the system. But if you, in fact, go and steal all the passwords, then you can take your time, fire up thousands to millions of machines or whatever else you want, and go and just decrypt everything and just announce in the end, okay, out of the 140 million passwords, we broke into 99% of them. And then you publish statistics to embarrass everybody with how bad the passwords are, right? So it's a very, very different kind of thing. This is why I'm very uneasy about storing, even with good methods, encryption here, okay? Okay, I wanted to mention something else, but slipped my mind. Okay, so let's talk about the rights management. Right, with this scheme, for example, you have to break into every single client, and which is much, much worse. Okay, so how do we do this kind of rights management? And this is the big question. Okay, let's think about how it's done in an operating system. So you'll get an account on department servers. And you probably notice that you can access some directories or files, and you cannot access some other directories and files. Some of them you can read, some of them you can read-write. Actually, when it comes to directories, you can even think there is a special permission called X, which is a search permission. Can you list the items in a directory? And it's actually possible to be able to, if you know exactly the name of a file, to access it, but not to be able to go and just do LSs in the directories to list it. But arguably, that's still quite crude, right? Now, you can take this kind of rights management, access management to particular resources. This has nothing to do with authentication, right? This is separate. You already are who you are. You can take it many notches over. And for example, think about a database. So if I have a database, I could consider managing rights not only to individual relations. So I have the database itself. Right, so let's think databases are a good example because they are everywhere. And they're a good way to both to get the job done in terms of organizing the data, running queries on the data, and to, in fact, control things. So if you have a database, you can consider doing things at the level of the entire database. That essentially means you can make a list. These users have access to the database. These users don't have access to the database. Done. Or you can do relation level. That means table, right? Right? So you can say, OK, you have 15 tables here. You can read these tables. You cannot read these tables. You can do something else, which I'm going to put in a second. But before that, I have to go in a different direction. Or you can consider saying, okay, not even relations. I want to do rights management at the level of every tuple, every row. Okay. Now, why row? Well, usually rows in a database represent facts, right? So for example, if I have information about, you have a single relation with information about students at the level of the entire university, I might need access, more privileged access, for example, rights access to students that in fact enroll in my class. So then you could say, okay, fine. For the students that are enrolled in my class, I have specific tuples that represent them. You can read those, but none of the other ones, let's say. Or you can even go one step further and say, you know what, you're going to get access or not get access at the level of even attributes or fields. Now, of course, the trouble is the following, right? You can consider all of these extremely fine-grained things, and that's great. But unfortunately, even if I want to do tuple-level access, the question is how. So imagine that I have, for example, at the University of Florida, I might have 5,000 faculty and something like 50,000 students. And if I have 5,000 faculty, 50,000 students, if I need to specify which faculty can see which records, right? I need some sort of a large matrix, and that's one way to do it, access control matrix. So if I would use an access control matrix, right, I would need 5,000 times 50,000, which is not a particularly nice table. It's an enormous table that might actually be much larger than the database itself. So you can't just go and say, I'll build these large matrices, because you easily get data structures that are larger than the database. Not to mention that manipulating these tables is harder now than manipulating the database. So now answering questions on the database is the easy part. It's figuring out who can do what. That's the hard part. So what I'm trying to say is you can consider all of these things, but if you don't find a very clever way to determine whether you have access or you don't have access, then you have at least a major performance problem or a completely impractical kind of system. So the idea then would be, can we come up with a much more compact way to specify who can do what, who has what access? Okay? So what we would like to do is, in fact, build up some sort of function, some sort of a computation, and the result of the computation can be yes, you have access, or no, you don't have access, but potentially have a much more structured way that depends on much smaller things in order to do such, to come up with such a conclusion. Yes, you have this access or you don't. So it turns out that in databases, there is a particularly nice and cute solution for this. Now, that's not, I mean, there are counterparts when it comes to file systems and other resources, right? But the database people just manage to get something really, really good, and it's what fits here in the question mark, right? In particular, views, right? So views are really, if you want, full queries, in which simply I can say, if I take, for example, I want to give a faculty access to records of all the students, but only the students that take the class. What I could do is take a relation that contains what students take what classes. Take another relation that says what faculty teaches what class at what time. Join between them will immediately give me this faculty has this person as a student. And then join with the records of the students, and that will give me, in fact, the records of the students that take the class that one of this faculty has. Now, you don't want to run the query. What you can do is essentially just provide a template for the query. That's called a view. And in fact, the template for the query, if you are going to take the database class, is going to provide even a neat way to perform some optimizations in the system, right? So in fact, what you're doing is you're creating a virtual relation that says student records for of professor blah, right? And the nice thing is, once you created this view, you can in fact do rights management at the level of the view, and then you only have the equivalent of rights management at the level of the relation. So if you bring these views to have the same power as the relations, namely you can use the views like you use relations, and the engine is going to substitute a part of the query rather than access a low-level relation, then you solve two problems. One of them is related to performance and convenience, because it's something that you probably want to do over and over again. But the other one is related to security, in the sense that it's very easy now to do rights management. So a lot of databases do not allow any rights management at the tuple and attribute field level. They only allow this kind of rights management, right? In which you can have relations and you can define views which are elevated at the same level as the relations. You can do rights management at the level of relation/views. Entire database, it's easy. You simply don't provide any login. And so this is one of the things you can do. Okay? Now, there is really no direct counterpart to this. Well, there is actually some sort of a maybe counterpart in operating systems in which you use some sort of symbolic links or whatnot to allow partial access. I'm going to come back to this later. But let me talk about another aspect of this kind of rights management, which is you usually don't want to control individuals. You want to specify these rights at a higher level. So normally, the way we organize everything is some sort of a hierarchical decomposition of the task, right? And this is the reason why we want to, in fact, have hierarchies like this one that we actually call some sort of protection domains. And we can have hierarchies among the users, which we call something like groups, right? So you can actually combine multiple such hierarchies to compute who has what rights where. So instead of specifying this specific user has a particular right done through this or any other mechanism, what you could do is say, OK, let's form something like groups, which is almost like virtual users, right? So you're going to say, the user belongs to a group, and I'm going to manage the rights at the level of the group. Because whatever I do, I want to give the same permission either to everybody in the group or nobody in the group. This is a reasonably powerful paradigm, okay? And it's used all over the place. This is why we have groups in normal operating systems, right? So then it's very easy, for example, to allow a user to extend its rights. You simply have, for example, a group that's called disk that allows low-level access to the disk. This is, by the way, an actual user used by all modern Linux distributions. So if I want a particular user to have access to anything related to the disk, which could be hundreds to thousands of independent resources, all I have to do is say, OK, this user now belongs to this group as well. So group management can be used as an effective way to do access management, right? So then you separated the problem. You essentially broke a complicated function that does this kind of a matrix or whatever is it that's doing into subparts that can be composed to compute if you have the right or not, right? So when you have a specific resource, for example, you can look at, OK, do I have right specification for groups? If yes, does this user belong to the groups? And you have to compute whether there is a combination that will allow access there. Now, the trouble is, if you're not careful when you're doing this kind of combinations, you can bump into NP-hard problems. And of course, you don't want to go there, right? So a very refined scheme that will allow access management has to balance these things. You want to make sure that the representation is as compact as possible. At the same time, you want to make sure that computing the function that tells you whether you have access or you don't have access to the resource can be done efficiently. And these things are not necessarily going hand in hand. You could have very compact representations that are actually computationally infeasible, okay? Now, I want you to know about something because it turns out to be very important. Well, it might have backdoors, but at least most of the people stay out of it. So when it comes to rights management, the more you control the rights in a fine-grained manner, the better off you are to resist various kinds of attacks, okay? A very interesting solution to this, all this entire rights management thing is secure Linux. How many people know about secure Linux? Right. Let's talk about secure Linux a little bit. Now, secure Linux, again, has nothing to do with authentication, has to do with rights management. So it's a particularly clever engine that can compute who has what rights on what resource. But it doesn't only allow specification of rights from the point of view of the users, but it allows specification of rights from the point of view of applications. So a particular problem in general is, if you want, illegal rights escalation. So what illegal rights escalation is all about is you find a way. So a lot of the attacks went on like this, for example, on Unix and on servers in general. You have a user that has low-level rights and somehow tricks the system to get much better rights, okay? It turns out that it's very hard to protect against this kind of an attack. If you need to protect against complete access control, you either have access to the system or you don't have access to the system, then all the cryptography helps. But if you have to make sure that a user, right, doesn't escalate its rights and pretend it's more than it should be, that's much harder. Now, a lot of viruses and so on need to do some sort of rights escalation in order to do serious damage to the system. And things can actually get very, very tricky with respect to this rights escalation, and there have been very clever security exploits in which a normal user can become a super user by just exploiting something. You somehow have to trick the kernel into letting you become a super user, okay? And even after tens of years, they still found ways to actually do this. Now, secure Linux provides a different solution. And it can actually, I believe, be extended even to things that go on the web. I'm not aware of anybody doing this, but in principle, it could be done. In secure Linux, you're going to provide rules, and a large number of rules, and the engine is going to compute from the rules whether you have access or you don't have access. But the trick is to come up with a language in which you specify the rules so that the problem becomes feasible, okay? So then what you're going to do is, for example, for every specific application, I don't know, even applications like, so imagine you have a web server, Apache. Right? Now, for various reasons, if you need to run Apache on a machine from the point of view of what rights Apache needs, at least when you fire it up, you pretty much have to make Apache initially start as in a root mode, in complete access mode, okay? So you have to be root when you start, and you're just going to trust Apache that is going to downgrade, at least for parts of the code, the rights to something lower, so it becomes less exploitable. So Apache normally, when it runs to run as a far less privileged user, and it's usually called Apache or Web or www or whatever. Right? But it has to start at root. Why? It needs privileged access to listening on ports that are below 1,000. Okay? So usually Apache listens on 80 or 443. Only the root can actually get control of ports below 1,000. And this is something that Unix systems do. Why? Because those are ports on which you have services running. So, for example, if you're not careful and you allow access to other applications to listen on those ports that don't have the right privileges, you could, in fact, knock out Apache, put your own user-level Apache, and then get all the traffic. And for example, when the users try to authenticate, they're going to send you the password in the clear, and you say just thank you, and you just put it in there, right? So a big problem in general in operating systems is who can access ports below a certain level, where most of the services are, okay? And then you have to do a rights downgrade, so access downgrade. But any mistake in how Apache is implemented potentially can be exploited to fool it not to downgrade the root and then have root access and do a lot more damage. Okay? Now, what secure Linux does is it doesn't only say, OK, Apache is root or is not root or has this user or another user. In fact, provides a complete specification of what Apache can access. So, for example, you can say, this application can only view and modify files starting in this directory structure and then deeper. If you do so, even if you exploit Apache, then all you can do is do something with the files that Apache was supposed to control in the first place and absolutely nothing else. Okay? So secure Linux requires a lot of effort because for every single application you have to go and determine what the application genuinely needs to access or doesn't need to access. And if you make a mistake, you simply can't use the application. But beyond that, you have much tighter security. And this is, by the way, secure Linux was developed in public domain by the NSA, National Security Agency, right? And it's used all over the place for their own systems. I mean, and also, it's one of the nicest results of type inference and type theory. Okay, so you're using one now, Scala. Okay, Scala at the core has an extremely good type inference engine, and this is why either it drives you nuts or provides a very secure environment. Another result of the type inference community, research community, is the secure Linux, right? So essentially, the theory developed in order to allow that very clever computation, whether you have a right or not have a right, is for this kind of type transformations, right? And it's type inference. It's almost like a logical system, but richer because it talks about types. And in fact, every time when you're trying to access something, that system tries to prove from the facts it has that you have the right to access it. And if you cannot prove it, it's in fact a proof system. If you cannot prove it, it doesn't give you the access. If you can prove it, it gives you the access. Okay. So It's an extremely elaborate, extremely sophisticated mechanism. But in the end, the community came together and came up with such rules for all the applications involved. And if you fire up secure Linux, you're going to have a pretty decent tie down on everything. Now, that's important because if somebody managed to trick the system, for example, even if you downgrade the access rights to something lower, even if you somehow escalate it, secure Linux will still prevent you from doing most of the damage that otherwise you would have done. Okay? So just keep that in mind. Do some reading on it. It's actually a very interesting kind of issue. Okay? So modern systems are going to use, I mean, first of all, you have to emulate groups, normal users, and the basic rights. But almost none of them have only this. There has been a big shift in the last decade to more refined methods. For example, it was actually spearheaded initially by Windows, in which access control lists started to show up. Access control lists are some kind of a compromise in between the full matrix and just very crude rights management. And once that happened, the Linux community started to pull some of these ideas in terms of access control lists. Then later, secure Linux popped up. Linux actually has multiple such mechanisms, and you can kind of switch between them, plus the basic mechanism in place, which is just the normal user rights management. Okay. Now, when it comes to, let's say, web applications, which is a very big concern right now. I mean, most of you, if you do anything, it's not going to be standalone applications. It's going to be some kind of web applications with servers in the back or clouds or whatever, right? Then this becomes even more important because you literally are going to have potentially millions of users. Right? If you have millions of users, millions of resources, none of these methods are going to work particularly well. Right? So imagine, for example, the situation that Facebook is in. Right? Literally, Facebook, maybe they don't do it quite well, but it's about rights management to a large extent. It's content delivery and rights management. Who can see what and when? And it has to be done in a secure way because otherwise people are going to find ways to exploit it. And there have been some high-level cases in which that happened, and it's not good, I mean, in general, right? So, for example, a particular point of contention is the fact that law enforcement has actually access to a lot of the systems. So they get some kind of privileged users that could, in fact, access almost everybody else's, or in some domains, Facebook pages. It's not quite clear what the relationship there is, for example. And these things can lead to a lot of mistrust and whatnot between the users and the company. So the way you do this kind of rights management, it's not only authentication. So authentication is one way to get in, but rights management, the way you do the rights management can make a big difference of whether, for example, the users trust the system or don't trust the system, right? So you can have the best authentication possible if you still allow some kind of rights escalation or you're not correctly protecting the resources in a secure way. Then I can just make a normal account on the system. I pretend that I'm some kind of whatever random guy. And using that, if I could just plug in the right URLs, because with that, I pass the first security check, and I'm at least allowed to access resources in the system. If I can then cook up URLs and get there, then it's a problem. So let's just briefly think about another possible scenario. These guys have an exam here, I bet. OK. Too many people outside. OK. So something that, I mean, to a large extent impressed me, because that suggests that I can trust them. So imagine you have the following kind of a problem. Okay? And this has to do, for example, with rights management. So think that you have, for example, pictures on Flickr. So I like Flickr because they increase the size to 1 terabyte, so I don't have to worry about it anymore. Right? I don't know how they make money, but that's their problem. So they increase the size, but hey, I have pictures with my daughter, which is 6. I don't want to put them in the web, but I want to send them to family. But what you can do is you can do some rights management in which you say, OK, sign up into Flickr, and I'll friend you or whatever that thing is called, and then you have access to see those kind of albums. But also, I would like to allow other people at least temporary access to some of those albums. Now, how could you do that? Well, it turns out that Flickr came up with a method, and it doesn't even seem hard to do. And their idea is basically to create something like secure URLs. So what you're doing is, if you want to give access to somebody to a particular album, they are going to create some sort of a link to the secure album through some very garbled and very long and hopefully cryptographically secure name. So one way to even do this kind of rights management, at least temporarily, is to generate, if you want, it's almost as if you form a single file and you allow people access to a single file, but that file through symbolic links leads to the real resource, right? So Flickr in particular is going to create a normal part of the URL and then really long number, which is probably some sort of it's almost like a secure session management kind of thing. You can actually manage it from Flickr and delete them and revoke rights and whatnot. And basically, getting access to that particular album, it's a matter of having the complete URL. Actually, URLs are funny things, if you've ever seen them, because part of them can actually be data, not necessarily files. Actually, almost nothing might be files. I mean, this is, for example, what PHP backends and whatnot do, is they take URLs and they extract function calls from URLs, right? So in the end, it's all an illusion what's a file and what's not a file. We had files in HTML for sure only in 1995. Beyond 1995, right, the moment you got some dynamic web going, you might not have files at all, in fact, but applicational functions and computational functions. So then, in a single URL, you could, I mean, the URL itself can be considered as proof that you have access to a particular thing, right? And this is an interesting way to do rights management. Because otherwise, how do you do it? You create users for people that don't even want to be users, right? I'm talking about people that don't want to sign up for Flickr, right? I don't know if Facebook does anything like this. I suspect no, because they want everybody to log in so they can brag that they have more users. Actually, this is one reason why I don't use Facebook, and I never go anywhere close to it, is because I all the time need to tell them who I am to even look at anything. It's tiresome, if nothing more, right? OK, so many other issues, which I don't have time to talk about, related to security. Even if it doesn't look like authentication or something else, security, cryptography can play a role to make sure that it cannot be forged. Is, for example, this kind of situation with access albums, right, in which you just create a secret URL. As long as there is no way to list what are the secret things known, and it's just some computation that happens into some kind of a server, that potentially is a very good way to do things. For example, the URL itself can be, imagine public key cryptography or something, right? The URL itself can, or even symmetric key. I can use on the server a secret key to take a nice data structure that specifies what is it that you're supposed to access, and to just encode that with a secure, my secure key, right? Now, all the security, good symmetric security algorithms will ensure the fact that nobody can forge any such message that makes some sense to me, and it's easy for me to validate that it is what it is. So you can cook up your own, for example, JSON data structure. You might even know exactly what I'm looking for. But in order for me to decrypt it correctly, you have to encrypt it correctly. And you're not going to be able to do such a thing. Now, something is there, though. You have to realize if that URL gets away, other people can access the resource, right? So proof that you can access the resource now, it's a large number, which plays its own kind of roles. I mean, it could be useful. It might be a disaster, right? Now, one thing that's also happening, I mean, I don't know exactly what the situation is there or not, but I think, for example, all of this illegal download websites are playing also all kinds of security tricks and tightening up the system. This is why they don't quite die. So the moment they manage to shut down something, something else pops up, and a lot of the access can actually be done through these secure URLs in which you simply have very long URLs that can actually be guessed. So somehow you have to be let into the club. There are some slides if you want to take a look at that, and you can read some more about secure group management, for example. This is one of the issues that you could do in secure group management, right? Cryptography and security community is quite large, and they produce many, many, many different interesting things, right? So again, last discussion about security, unless something interesting happens on the web by the end of the class. Never build your own low-level security mechanisms. Be more concerned about how you compose them and whether you have gaps or not in the security protocol. You have to implement your own security protocol, at least at the very high level, right? Use this here, and talk through whatever channel, okay? All right. We're going to have a quiz over the weekend about security, and we are going to talk about distributed file systems on Tuesday, and then for other lectures we'll see.